Ladies and gentlemen, welcome to today's lecture. I hope you're enjoying the weather as much as I do. Typical northern Germany fall weather, windy, wet, cold. Isn't it wonderful to study? That's a reason to study. So we continue the lecture today. I started last time with deductivism. That's the position that is an answer to the problems of inductivism. Inductivism has its problems, we discussed them. Deductivism is an answer, and the main idea of deductivism is that in order to make sure that the general hypothesis that you want to have in science, that these general hypotheses are somehow solid, valid, good hypotheses, that science devises tests to test these hypotheses. So the general direction of scientific research, in a sense, is not, as inductivism describes it, bottom-up, that you start from observations and generalize them in order to reach the general hypothesis, but it is top-down, that you start with general hypotheses and then you test them and try to eliminate those that you don't want to keep and keep those that survive the test. That's the general idea. Now, in order to make this general idea running, one has first, from all the possible hypotheses that can be formulated, one has to take out a subset of this hypothesis, namely those hypotheses that can indeed be tested. So we must eliminate those hypotheses that are of the structure, like my standard example, the universe is governed by love and hate, namely hypotheses that are very general, that's not a disadvantage, but are formulated in a way that you cannot imagine anything happening in the universe that shows you that the hypothesis is false. And a hypothesis that cannot collide with empirical data is a hypothesis that is called non-falsifiable. And what we want to have in science is hypotheses that are falsifiable, meaning that they can collide with scientific data. So the first step in the development of this position of deductivism is to formulate what is called a demarcation criterion. And the demarcation is a demarcation between scientific hypotheses and other hypotheses. And these other hypotheses may be religious hypotheses, metaphysical hypotheses, pseudoscientific hypotheses, and the like. Right? So the position started to be developed by articulating this demarcation criterion. And as I said, the demarcation criterion states that a hypothesis is only admitted in the realm of science if it admits serious empirical testing, meaning that it is formulated in a way that it can collide with empirical data. So that's the first step. The second step then is to show how this empirical testing of such general hypotheses is actually done in science. And that is the second step, the concrete testing procedures. Now, the logical tool that is used for testing of general hypotheses is normal logical deduction, to deduce something, as you are used to it in mathematics or in everyday life. If we have, say, two premises, all men are mortal, Socrates is a man, then you can deduce Socrates is mortal. So that's logical deduction. You are quite familiar with it. Logical deduction is comparatively unproblematic. If you think about it very hard, there are many, many areas in which logical deduction is fairly unproblematic. So if you use it as a tool in science or in philosophy, you are having a rather solid foundation, right? I'm saying that because the counterpart that we encountered in inductivism, namely inductive generalization, is risky, right? That was the problem there. And therefore, deductivism says, come on, we avoid all these problems of inductivism by just not using inductive generalization, but we use deduction, and deduction is something solid, we understand, and it's quite sure that we don't commit mistakes with doing deduction. So that's the general idea. Now the concrete application of deduction is that the testing of general hypothesis functions in the way that you deduce something from these general hypotheses that can be compared with empirical data. That's the main idea. It's very simple in principle. Of course, it may be quite difficult in practice, that you deduce something from the general hypotheses. I gave you the example of the ring structure of benzene that Kekulé discovered in the year 1865. I had a look at the literature, but I'm sorry, I didn't have enough time because I was in the meantime in Canada at a conference and I had other things to do there. But today, just before the lecture, I had a quick look to find something. It's simply that different chemical properties of a molecule like benzene depends on the molecular structure. So you have there are I think 260 possibilities how you have the sum formula C6H12, which is the chemical formula for benzene, how you can arrange them. And the chemical properties of a molecule, of course, depend on the structure of the molecule. So what you have to do, you deduce from, for instance, the ring structure of benzene, you deduce certain properties that the molecule should have if it has the ring structure, and then you compare what you deduced from this model, compare with empirical data, and then either these data are in agreement with what you deduced or they're not in agreement. And if they are in agreement with what you deduced, then you certainly haven't falsified the model, but you say, okay, the data are consistent with my model. So that's the general idea of deductivism. Deduce from your general hypothesis, be it a model, a theory, a law, whatever it is, deduce something which you can compare with empirical data, then do compare it with the data, and then you either get an agreement or a disagreement, and in the case of disagreement, the hypothesis, as it is called, is falsified. It's shown to be not in agreement with the empirical data, therefore the hypothesis cannot be true. That's the general idea. So we came to this point in the last session, and I think I showed you this with the example of Ohm's law. And this was the final line. Then if the measurement differs significantly from the deduced values, the hypothesis failed the test and it is falsified. Otherwise, it survived the test. This is where we ended last time. Did any questions come up in the meantime you would like to ask now? No? Okay. Then we continue. And here is the story that will be developed now in the next slides, that hypotheses are kept in science as long as they have not been falsified. Right? This is a rather negative statement, negative sounding somehow, but that is the spirit, and I'm developing the spirit in a few minutes further. This is the spirit of deductivism, of that position. They say, look, that's all we can do. We do not get something very positive about hypotheses, but we only get that they survived a certain test. And that's all one can get. You can't get more. It's a dream to have more. So to have something like in mathematics, you have a positive mathematical proof for something. Mathematics is very different from natural science. In mathematics, we do have the possibility of presenting definitive proofs, given, of course, the axioms. And then we have a positive proof for something, and then we say, we are certain we can keep this theorem, as it is then called. But in science, as we are then in a realm where we don't have these a priori proofs, they simply don't exist. We have data, and we can confront hypotheses with data. So we are in a somewhat less fortunate position as in mathematics. Therefore, mathematicians, many of them, do not really like empirical science because no proofs exist. And a mathematician is only happy if he can produce a proof for a theorem. Otherwise, he's unhappy or she's unhappy. So in science, we don't have these proofs, and we have only this somewhat negative attitude, as deductivism describes it, that hypotheses are kept in science as long as they have not been falsified. And all you can do is trying to falsify, and then you either falsify, then it's out, the hypothesis is out because it's shown to be false, or it is kept and waits for the next empirical test. Okay. Now, let me say a little more what that implies regarding the fundamental question of general philosophy of science. Remember, this fundamental question was, what is science? Simple, very simple. What is scientific knowledge? Tell me what is specific about scientific knowledge. Why is scientific knowledge better than other forms of knowledge? And the answer then that is given by deductivism is this. If you look what science is, then the answer that deductivism gives is science is the continual invention of falsifiable hypotheses and their critical empirical test. Now, look at that. That is called an invention of falsifiable hypotheses. I told you that in deductivism, the scientist is very free to, as far as the generation of hypotheses is concerned. You are free, as I told you with the Kekulé example. He was free to invent a certain structure of the molecule. He didn't know what it was, so he invented a hypothesis, dreaming, or his son might have told him the hypothesis. It happened that he dreamed it up. That's irrelevant, right? The scientist is free to invent the hypothesis. The only restriction being that the hypothesis must be, in principle, falsifiable, right? In order to be a scientific hypothesis, it must be possible to test it empirically. If it's a too general hypothesis that is almost empty, then it cannot be tested, then it cannot be part of science. So it's the invention of falsifiable hypothesis, but then the next step is, of course, is the crucial one after the invention or dreaming up of a hypothesis, namely really putting it to very critical empirical test. And that's exactly what happened in the Kekulé case. After the dream, he went back to the lab and started testing the hypothesis by, as I told you, deducing consequences from the hypothesis that can be confronted with empirical data. And that's exactly what he did. So he deduced from the ring structure certain chemical properties that benzene should have, and then he measured the chemical properties and showed, well, there is agreement of the data with what he deduced from the hypotheses. And you could, of course, from other structures of benzene, you could deduce other hypotheses about the chemical properties, and then you could show they were not fulfilled, the empirical data were different from them, and therefore we got a sort of confirmation for the general idea that benzene has a ring structure and not another structure. So this is, so to speak, the short answer to the question, what is science? Science is the continual invention of falsifiable hypotheses and their critical empirical test, and of course, depending on the outcome, the keeping of the hypothesis in science or the dismissal of the hypothesis and throwing it out from science and saying, sorry, you are falsified, bad luck. Okay. This is this negative spirit that I just mentioned, that science in the view of deductivism, right? That must not be that's not necessarily the ultimate truth, but I'm presenting you the position as deductivism describes it. And I hope this is plausible, right? The criticism comes later. So science in that view of deductivism does not try to confirm hypotheses, trying to find positive evidence for a hypothesis. Deductivism thinks that's the wrong move, that's the inductivist move, and it doesn't work. And therefore science does not try to confirm, but try to disconfirm them, to falsify them, right? Only a negative movement. Here's an hypothesis, and I'm the scientist, I'm going to show you are false, right? And if that is not possible, if it survives, then I say, fine, you may stay. And then the next scientist comes, I show you are false, right? It's a very negative sort of attitude, but wait a minute, that's not too negative if you get the full picture, which I'm describing in a second. This is the picture. If you think what sort of mindset scientists are in, then there is something which, at least in the Western tradition, is something very positive. Namely, the spirit of science is fundamentally critical, right? In different traditions in different countries, in your home countries, for instance, it may be that criticism is not something which is valued very positively. For instance, in the family or in the clan or so, it may be that criticism is not an attitude that people like very much. But in the Western tradition, in the Western intellectual tradition, not in the church tradition, of course, but in the Western intellectual, scientific, and philosophical tradition, to be fundamentally critical is generally valid, it is generally valued as positive. Not always, not against the state, for instance, or against democracy. If you're very critical about democracy, you will have a hard time in Germany or in the United States. So if you say, no, democracy is nonsense, I want to have a really strong dictator. That's, if you are critical of democracy in that sense, well, that may be a little difficult. And you may not have public good positions then. But anyway, this is something that if a scientist reads this or understands this position of deductivism, he or she says, well, yes, that describes me in a very valuable and adequate way. I'm a very critical person, that's positive. Yes, I'm a scientist, I'm critical, wonderful, deductivism, that's my game, right? And if you describe then science because of this spirit, then you can say that science tries to be as unbiased and dogma-free as possible by testing all proposals as severely as possible. Right? And that sounds to Western ears wonderful, and probably to your scientific ears as well. Yes, who loves dogma? Nobody loves dogma. Okay, churchmen perhaps. But dogma in science, no, we don't want that. Who likes bias? Nobody likes bias. Of course, we are as biased as possible and dogma-free as possible. And we do that in science by having possibly wild hypotheses. Yeah, you dream up something wild, like this ring structure of a molecule. Nobody has ever thought of that, but still it may be true. And then so you are allowed to dream up wild hypotheses, but you've got to submit them to severe testing. And by this testing procedure, you remove all the crap and nonsense. And what remains is good scientific stuff, you know, well tested, falsifiable, and you're eagerly waiting for the next test because you are so critical and undogmatic. So that's the spirit of science that you get. And I think, as I said, I mean, at least for people in the Western tradition, this is a very attractive picture of science. And for you, I guess, most of you, this is by now also a very attractive picture because you underwent a scientific education. And this is what your teachers and professors told you all the time. You know, you've got to measure and not have prejudices and blah, 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 and all that stuff that comes out here in a very straightforward sense. This idea then, and Karl Popper is one of the inventors of deductivism, and I come back to the person in a later section, he has well expressed this general idea of what science is by the title of a book he's written or published in '63, Conjectures and Refutations. Conjectures, if you don't know the word, are, so to speak, guesses. You guess a hypothesis, you dream up a hypothesis, it's a conjecture. And then come the refutations, the showing by empirical tests that they are false, right? And the surviving stuff is kept in science. It's only by, so to speak, a negative procedure. You try to remove it by severely testing, but those hypotheses that survive, they are kept in science, well, at least until tomorrow, right? When the next test comes, and then it's possibly eliminated. So this is this general idea. It's an idea, as I told you, that avoids this problem of inductivism, namely that step of generalizing from the data. It avoids it because it says, deductivism says, well, there is no generalizing step. You may get your hypotheses in any way you want. Some people may say, oh, I study the data, I study the data, I study the data, and here's my hypothesis. Other people may not proceed in that way. And deductivism is very liberal here because deductivism says you are free, right? How to get your hypothesis. The main point is that you test it afterwards. And the procedures or the ways or the associations by which you gained an hypothesis are simply irrelevant. Relevant is then that the hypothesis is falsifiable in principle and that you try to falsify it by testing it empirically. Okay. All right. So far, so clear? Any questions so far? Good. Now the next thing is a consequence, and that's a word that you possibly don't know, fallibilism. Fallibilism, and I'm going to explain that word in a second because it's not a very common English word. Now, this is a consequence now of the procedures that I delineated how inductivism describes science. And that's a consequence that is possibly a little strange, but possibly something we really have to live with. Namely that in spite of all these critical tests that you perform in science of a given hypothesis, this hypothesis never becomes absolutely certain if it has passed all of the tests without being falsified, right? You have the hypothesis, it undergoes tests, and you test it and test it again. But you can never be certain that the hypothesis is true because you have tested it so far, it has survived the tests, but you don't know what's happening tomorrow. right? Tomorrow you may devise a different test, and then the hypothesis may not survive that test. So you never reach certainty. That is something, well, it's here again description, that a new test will be devised which falsifies the hypothesis is never excluded. You cannot exclude that. There, science is different from mathematics. If you have a mathematical proof, if you have a certain set of axioms, and you have a certain statement, and then there is a mathematical proof, which means a logical deduction of that statement from the axioms, then you can be sure, for good, that as long as you keep these axioms, the theory will be true relative to the axioms. And this is mathematics where you can establish that sort of absolute certainty. In the empirical sciences, we cannot do that, and deductivism tells you why, right? It's not enough just to say, oh yes, in science we cannot have no proof, so okay, let's continue. You've got to also understand why it's not possible to have absolute truth in the science. And deductivism gives you a very convincing story about that. Namely, you start with the hypothesis, you test the hypothesis may survive the test, but that's no guarantee that tomorrow another test will be devised that shows that the hypothesis is false. That you cannot possibly exclude. And that is the reason then why hypotheses in the natural sciences or social sciences cannot be proven, because we simply have no instruments. We have only the critical tests by data, but we have no positive instruments that can prove a scientific hypothesis. And that means, as a consequence, scientific knowledge never becomes infallible. And infallible means absolutely certain. Fallible means it may later to be shown to be false. Right? The fallibility says it has the possibility of being false. Right? Infallibility means being absolutely certain that it's true. So we have to live with that consequence, therefore fallibilism. That is something, by the way, that is in natural science a comparatively new insight. If you look at science in a historical perspective, on a very long range perspective, starting then 2,500 years ago, when the beginning of mathematics, astronomy, and philosophy, all that started in ancient Greece, then for a very, very long time, the idea has always been that science produces knowledge with one particular characteristic, namely to be absolutely certain. Right? The ideal of science for 2,400 years, out of these 2,500 years, has been the hallmark, the characteristic of scientific knowledge is that scientific knowledge is absolutely certain. Right? That's the best form of knowledge thinkable. Right? That was the idea. The model was mathematics. Right? The model for all science has been, for most of the time of science, been mathematics. Why? Because in mathematics you can produce proofs. Right? And the proofs establish the absolute certainty. And therefore, also for the natural science, the idea was that it should be able to produce scientific knowledge in the sense of certain knowledge, right? Absolutely foolproof. The point simply is, and this was then an insight from the late 19th century and beginning of the 20th century, the historical details don't matter really, it has much to do with the development of physics, where people who had believed for 200 years that the classical physics, Newtonian physics, that started to develop in the 17th century and during the 18th century, that people finally found, well, we developed this sense of certainty that science produces infallible knowledge, namely classical mechanics and classical electrodynamics, and then at the end of the 19th century and the beginning of the 20th century, it turned out that even that knowledge was not infallible, and it was shown then by the development of two new theories, especially by special relativity theory and by quantum mechanics, that the classical physics was really not infallible, but it was false if you look at certain ranges of energy and certain ranges of distances. It just doesn't hold. If you describe an atom, then classical mechanics just breaks down, and you need a different theory, quantum theory. At any rate, the insight was then, oh, We only produce in natural science fallible knowledge, knowledge that may be false. We don't know it yet, but it may be false. And the idea that science could produce absolutely certain knowledge is simply an illusion. And that's the insight of the last 120 years or something, and which you find, of course, the horticulture people, which you find when you get this sort of schema how to describe your research project, right? Hypotheses and tests, right? And procedures. That's already, you are not devised to say, give your axioms and then give a proof for your hypotheses. That's what the mathematicians would do, but you don't do that. Because now, in the 21st century, everyone in natural science knows there is no way to reach absolute truth, infallibility. But it's only possible to have hypotheses and test them, and the best is that the hypothesis survives, but that doesn't guarantee that it survives tomorrow's test, right? That's the idea, and that is in deductivism, that's a very nice consequence flowing naturally out of that philosophy, which makes it very plausible that you say, okay, I understand now why science is unable to produce infallible knowledge, absolutely certain knowledge. Well, because it works the following way: hypothesis, hypothesis testing, blah, blah. No inductivism, no inductive generalization, doesn't work anyway, but only this deductive testing, very safe. So we refute hypotheses, they leave science, and we are left with the rest, namely those hypotheses that have yet not been falsified. And that's all we have, and there's not more to have, right? So it's a consequence. Fallibilism and deductivism gives you a wonderfully intelligible and plausible explanation for that fact of science. Okay, scientific knowledge is bound to be fallible, right? No way, no alternative. Now, and well, I already said that this insight rejects the predominant Western ideal of science from antiquity up to very recently, according to which scientific knowledge should be infallible, namely absolutely certain. All right. According to deductivism, also that on this slide here, I said already that scientific knowledge consists of hypotheses that are accepted until they are falsified. And that's another consequence here that is important in deductivism, and which is probably also plausible if you simply look at your own experience in science, that science is an intrinsically dynamic enterprise, as hypotheses have to be continually tested, right? We have a slight problem here, as you will see then in a minute, that we cannot give up testing because we never reach a stage where we can say, finish with testing, we are absolutely sure, right? As you know, tomorrow's test may show you that your hypothesis is false, and since you do not want to live with false hypotheses, you want to have certainly not false hypotheses, you must say, oh, here's a new test available for my hypothesis, I've got to test it, right? I've got to do that. And therefore you are always on the move with the hypothesis that you cherish or like or want to apply or want to predict with or whatever, that you are forced then to say, okay, where's the next test? And then you're going to do the test. By the way, that may sound, in some contexts, it may sound a little funny, and you say, well, that's not really how I work from every day to every day. But I give you a different example which is wonderfully fitting this idea. There is this fundamental idea in physics that the velocity of light is a universal constant, right? And that has been measured to a very, very high accuracy, something like 10 to the minus 10 relative accuracy, which is pretty good, right? But whenever a new method of measuring the velocity of light is invented, it is immediately used in order to test the hypothesis of the constancy of the velocity of light. Although every physicist today is really deeply, deeply convinced that the velocity of light in the vacuum is a universal natural constant. Really, everyone believes it very firmly. My guess is some physicists would bet a large amount of money that this holds not only for the relative accuracy of 10 to the minus 10, but really 10 to the minus 20, or absolutely. Well, if you are here a deductivist, you'd say, boys and girls, be a little careful. You have tested it, up to the relative accuracy of 10 to the minus 10. We do not know what's happening if you test into the accuracy of 10 to the minus 11. You don't know it. So if you can test it, you've got to test it. And in fact, that's really a fact that whenever, as far as I know, I haven't systematically researched that, but from time to time you see that in the scientific literature, this is something which is certainly worth a paper in Nature, right? Nature, the most prestigious journal in the natural sciences, general natural sciences. And if someone comes up with a new test of the constancy of light by pushing the error limit, say, to 10 to the minus 11 or 10 to the minus 12, that's certainly something people then do, and of course they are relieved, and they expect, of course, that the test will say, yes, the velocity of light at vacuum is a universal constant, and this is the value, right? But that test is being done, and and that is very nicely described by fallibilism, because it tells you why you cannot be certain beyond that what you have already tested. Okay. And if you push that to the extreme, then that would mean that to stop testing hypotheses is to stop doing science. So if you simply believe, say, the constancy of light, constancy of the velocity of light, and say, yes, there is a possibility of testing it to a higher accuracy, and you'd say, no, I won't do that. That's too, I don't feel like it, or it's too expensive or so. Then deductivism tells you, then you stop being a scientist, because you then simply accept as a dogma that the velocity of light is a constant, and you don't test it any longer. And once you have the possibility of testing it, you must do so. So science has an inbuilt drive, so to speak, that you have to continue the activity, right? Your supervisors do the same with you, with your master's thesis, I hope so, right? They push you, continue, and start testing, and look how big your sample must be. So you can understand your supervisors now much better with deductivism. So you see how important philosophy can be, right? Okay? Do I mean that seriously? Yes, partly. Okay. All right. Okay, that's basically the position. I now make an historical remark that you see how this position was developed, that I keep that very short. And then, as you may imagine, I come to the critical remarks, the problems that deductivism faces. Now, deductivism was developed in the 20th century, mainly in the work of a guy called Karl Popper. That's the guy, he's an Austrian, but then he left Austria during the war, went to New Zealand, and then came back to London, England, and there he became, then after the Second World War, became world famous. He covers really the 20th century, and he's a very important philosopher of the 20th century. Now, it is not an accident if you look when he lived, and he started developing deductivism in the 1920s and 1930s. And if you recall, special relativity was developed in 1905 by Albert Einstein, and quantum mechanics was developed in its more or less final form in 1925 by several people. So that was the idea where we had this in this first quarter century of the 20th century. We had this sort of revolution in physics where it became very clear to the physicists that infallible knowledge is not to be had in physics, as one had believed for 200 years in the infallibility of classical mechanics. And then people woke up from this dream, so to speak, and realized, sorry, that's not possible. And Karl Popper was the philosopher who first then articulated that experience that physicists, of course, had primarily, but Popper then had also studied physics and was interested in physics. And he then tried to build out of this experience of fallibility this deductivist position. And also he was quite influenced by the criticism of inductivism, especially that it's impossible to justify the inductive step from data to a general hypothesis. So that's the background. It's therefore not entirely uninteresting to know this figure here when the guy lived, because it tells you something about his intellectual background, about his intellectual context. And the context here is quite obvious, that he developed the position in the 20s, because then the sciences had reached a stage where it was, so to speak, real time to develop a position that accounted for the fallibility of scientific knowledge, because that was the experience people made. Many scientists, including social scientists, even today, adhere to this position. So this position was especially successful in the social sciences, which had always methodological problems, and then Popper came and had written his wonderful book, The Logic of Scientific Discovery, and then the social scientists said, oh, that's wonderful, now we know how to devise our science, how we do sociology, for instance, or social psychology in a way that how the sciences, the natural sciences do it, so we can copy the methods of the natural sciences. If you work in economics, as some of you do, then you may know that of course the economists also took over large parts sometimes from the deductivist position by saying that's the way how we can gain the reputation and the solidity, for the social sciences, for economics, that the physical sciences so nicely represent and are therefore admired by everyone by producing this wonderful knowledge. And we social scientists, we don't know really how to do that, so let's copy the natural scientists. And the blueprint to copy was given by this book, namely by deductivism. And as I try to present it to you, it looks very plausible, very suggestive. You know what you're doing, and you're getting a picture, an image of yourself as a scientist. That's a picture that you like. And of course, the acceptance of a philosophical position also depends on how yourself are described, right? If a philosophical position describes every scientist as an idiot, a dogmatic idiot who is mean and bad, then nobody would accept this position in the sciences. Yeah? That can't be true, I'm a good man, right? But that's of course not an argument, but it just tells you that you understand some sort of sympathy that this position generated, and it's not a groundless sympathy, but it's really, it is a valuable picture of science until it encounters criticism, which comes very soon. Now, this position is also called falsificationism or critical rationalism or the hypothetical deductive account of science. Now, falsificationism is plausible, right, because you try to falsify. Critical rationalism would take me 10 minutes to explain to you, so forget it, it's not necessary. But this one again, you understand immediately, hypothetical deductive account of science. The hypothetical meaning that you come up with hypotheses, and then what you do is you deduct something from them. That's the logical step, deducing something in order to put it to test, right? Therefore, this is a very short and descriptive name. It's a really descriptive name of what deductivism amounts to, namely the hypotheses and then deducing and then testing. All right. Okay. Any questions so far? No? Is it a plausible picture of science? Are you now all deductivists? I'm saying now, finally I know it was worth coming to Hanover because now I know what science is, right? Is that the case? Hopefully so. Okay, so let's destroy it. Okay, now we look at some problems. I mean, it looks as if deductivism has solved all the problems of inductivism, right? That's why we developed the position, because inductivism has its fundamental weaknesses, and therefore deductivism was developed, and that's also historically true. If you read the work of Karl Popper, that's really true. He wanted to have an alternative to inductivism because inductivism doesn't work. So he developed this position, and it seems to be we solved all the riddles of the world. We know what science is. Wonderful, we can home and sleep. Unfortunately, that doesn't really work. Why does it not work? Well, there are some problems. Now let's first again look at a specific feature of deductivism that seems to make it especially attractive, and that is that it's something very, very abstract now when you read it here. Deductivism seems to successfully exploit what is called the asymmetry between verification and falsification of general hypotheses. Okay, general hypothesis is clear. We talked about that from the very beginning. We need them in science. And then there seems to be something which is an asymmetry, meaning that the two things are not treated equally, namely between verification and falsification. Verification of a general hypothesis is showing that the general hypothesis is true. Falsification is showing that the general hypothesis is false. And the statement is there's an asymmetry, right? It's somewhat different between falsifying and verifying an hypothesis. So what does this asymmetry consist in? It consists in pressing this button and nothing happens? No. Here we are. It consists in the following. The verification of a general hypothesis, a definitive proof of its truth, is impossible. Right? Verification means show that it is true, really show, demonstrate it, right? And that's in the empirical sciences, unfortunately, not possible because we have infinitely many cases, and we cannot run through infinitely many cases in finite time, right? Unless the time shrinks faster than the expansion, but that's a mathematical trick that doesn't work, right? So it is not possible to verify a general hypothesis because infinitely many tests would be necessary, and that we can't perform. That was the problem of induction. But the definitive falsification of a general empirical hypothesis seems possible. Why? Because you need a single fact that contradicts the hypothesis. One single case is enough. Now take this very simple example of all swans are white, right? If you want to verify it, you've got to run through all the swans in the universe, right? Look at it. Are you white? Yes, thank you. Are you white? Yes, thank you. And go through all the swans in the universe, not only today, but also in the future, okay? That's a very long story, even for a master's thesis. That's too much work, okay? But if you want to falsify the hypothesis, it means you have to find one single swan. So what do? You buy a one-way ticket to Australia, right? Go there, look at that black swan and says, here you are, right? Hypothesis falsified. By one example, right? And then you telephone back and save the money for the return flight, okay? Thank you. Okay, so you see the point, right? That's the asymmetry. For the verification, you need infinitely many cases, and for the falsification, you need only one. And that is what deductivism exploits. Deductivism says, well, that's the trick. We don't even try to verify general hypotheses because we need infinitely many cases. That's not possible to do. But what we can do is we can definitively falsify hypotheses by having one counterexample, right? By one single case. And that's the asymmetry, what I describe here. And therefore, deductivism is so attractive because it tells you you can avoid this damn problem of inductivism, which tells you, yes, to have more and more and more and more and more data, and it never ends, right? And you can never definitively prove it, but what you can do, you can definitively disprove it. And therefore, you should turn around in science from deductivism away from the idea that you have to have positive evidence, showing the truth or confirming or making it plausible that a hypothesis is true. No, says deductivism, that doesn't work. You've got to do the opposite. You've got to try to show that the hypothesis is false, because that you can definitively establish. Right? That's the idea. So what deductivism does is, and now possibly you understand the sentence a little better, because it exploits this asymmetry. It lives from this asymmetry by telling you, forget it about this verification. It's not possible, doesn't work, right? We can't do it, but here's something we can do as finite human beings. We have one counterexample, and then we can eliminate definitively a hypothesis, right? And what remains with us are hypotheses, of course, that are fallible, but we continue testing them, right? So there seems to be a very special attractive feature of deductivism, similar in attractiveness, as I described to you, inductivism, where the attractiveness was that we start with something that's theory-free and therefore practically certain, right? By doing theory-free observations. That looks good. You say, okay, that's nice. We start from something which is really certain, and then we build up, right? That was the attractiveness of inductivism. The attractiveness of deductivism is somewhere else, because that dream of inductivism has evaporated. It doesn't exist. These theory-free observations, don't exist. And even if they existed, the generalization wouldn't work, really. So we've got to give that up. And deductivism says, yes, but I have shown you something else that's at least as attractive. And that is this asymmetry of falsification and verification. And therefore, we got a turnaround from verification, from a bottom-up verification to top-down falsification. That's the trick. That we exploit, and then we get a philosophy of science by which we really understand how science works. So that's the idea. And I hope this is plausible to you, because I'm bringing this description here under the title of Problems of Deductivism, because unfortunately things are not that simple. On closer inspection, the situation is more complicated, and that is where the break must come in. Then we have a very nice cliffhanger, and within 8 minutes or so you reconvene here, and then I continue.